So, welcome back after the small break. I think we are going to continue. So our next speaker is Andrea Mohr, who is going to be talking to us about the stem cell grafts.
Therapy for the treatment of cancer. We are establishing this therapy for several types of cancer, but our main focus is on advanced prostate cancer, like Greg already mentioned. But before I talk about our research, I would like to thank the organizers, and I found this on the internet, all wearing lab coats on square 4 things, so amazing. Thanks very much for the invitation, and thanks for organizing such a fantastic event. I already had so much fun tonight. And now I would like to tell you something about stem cells in general. Stem cells are, what they do, so a little bit about stem cells, and then moving on to the stem cell type I'm particularly interested in mesenchymal stem cells. These are a special type of stem cells which we then plan to use in cancer therapies. And as promised, I start with the concept of stem cells, which dates back to the 19th century, when science was mainly looking and describing phenomena and nature. And that was done here by hematologists who looked at a blood smear, and what they saw was different types of cells in the blood, like platelets, erythrocytes, immune cells like monocytes, neutrophils, lymphocytes, and they were fascinated by this. But they didn't know how these cells develop, and then they started to speculate about the existence and properties of progenitor cells, of stem cells. And of course they didn't have the technology in place to identify and characterize stem cells, but they speculated about it, and they came up with the hypothesis that there must be a common ancestor cell, a stem cell. But it finally was in 1963 when Becker and McCulloch and Till published this paper. This was basically the birth of stem cell biology. They identified the hematopoietic stem cell and characterized the cell, and their work was the launch pad of stem cell research. From now on, stem cell research was born, and this is evidenced by the number of publications. I took the year 2000 when I started stem cell research, quite a while ago. There were only about 3,000 papers available in PubMed. This is the database we're using to look up papers. And now this year there are already over 500,000 stem cell papers published. So this is an ever-expanding, exciting field. And this is also evidenced by the emergence of dedicated journals, dedicated stem cell journals, like the most prestigious one, Cell Stem Cell, and others like Stem Cell Research and Stem Cells. So with this discovery, stem cells have become the object of an increasingly intensive research effort over the last few years. They also made it out of the scientific community into the public limelight. So they are on different news magazines and newspapers, and there are even children's books about stem cells. And surprisingly or positively, they are mainly associated with positive terms like treatment, breakthrough, cure, hope. So all these positive things are associated with stem cells. But what are stem cells? So now we come to the cells themselves and what makes them so attractive. Stem cells are described as the body's master cells, building block of the human body, cells whose functions have not been decided. And this is based on one characteristic which makes them attractive. It's that they can divide and renew themselves over a long period of time, so they don't die out. They always stay young, they proliferate, and they can give rise to all types of cells in the body. So they can differentiate into 220 different cell types. And that's what makes them attractive for researchers. Because you have these cells, you differentiate them, and then you can basically, in the future maybe, replenish all organs, all tissues in the body. And this is why the stem cells found their way relatively rapidly into the field of regenerative medicine. But this is not where we want to use them. We want to use them in cancer treatments or cancer biology, and this is based on the fact that they play a role in cancer development. But let's have a look what cancer actually is. When I ask you, you're of course experts, and you will come up with the most up-to-date term or definition that these are cells which show uncontrolled cell growth. But I want to take you back a few years and I want to acquaint you to a historic definition. Cancer is a wound which never heals. And this term has been coined by Dvorak, who observed that cancer can appear in different forms and shades, and in case of skin cancer, it looks like a wound which doesn't seem to really close, and it's opening up again, and it doesn't disappear. So that's why he associated with wound healing and wounds. And later on, when we looked at the scientific, the signaling cascades taking place in cancer, we could see there are shared pathways. Cancer uses pathways of wound healing, and this is because stem cells play a role in cancer development and in wound healing. Stem cells have been shown to home to injured tissue and try to replace damaged tissue, and that's what they do in the case of cancer. They sense the cancer in the body, they migrate towards the cancer, they integrate into the cancer tissue, so they're part of the tumor microenvironment, and they try to repair the tissue. And that's part of their normal function. And this is one specific cancer cell type which does that, the mesenchymal stem cells. And here we are. These are the ones we are working with mesenchymal stem cells. These are the second stem cell population in the bone. So you have the hematobolic stem cells on the one side, and you have the mesenchymal stem cells on the other side. And they can be obtained by bone marrow aspiration. So you take you need puncture in the bone, into the bone. You take the bone marrow, and then you put it in a tissue culture dish in a normal low glucose medium and wait for minutes. And what happens is the other cells die off. Yes?
Could you keep the microphone in front of your mouth? We can hear you very well with the microphone in front of your
Okay,
mouth, but it's moving a bit.
Okay, sorry. Yeah, thank you. So what happens after couple of weeks, these cells grow out as colonies. So you finally can grow them in tissue culture dishes. And they can be then expanded and readily harvested. So the advantage of this stem cell type is you can expand them. You cannot do this with other stem cells, or not with hematopoietic stem cells, because they die off. They are only short-lived in culture, in contrast to these guys. And this is an image how they look in tissue culture. They are like they grow like fibroblasts. They have a fibroblast-like shape, and they nicely grow in tissue culture. And when you change the medium to differentiation media, like we've done here, they differentiate. And that's what they do. Here we have them in adipogenic medium, and they develop into fat. And this is evidenced by these red vacuoles, because we stake them in red. And these are lipid vacuoles, so they can differentiate into fat. And this is called adipogenic differentiation. They can also differentiate into cartilage when they differentiate along the chondrogenic lineage. And this is shown here. The cells condense and change their morphology. They form little pellets, like cartilage basically, in your culture plate. And the most dramatic changes happen during the osteogenic differentiation. You end up with bone in your tissue culture. They include mineral deposits in the culture, and they're really hard to see under the microscope, because it's basically bone tissue which developed. So from these images, you can imagine why they're so interesting again for regenerative medicine. In our case, we don't want to differentiate them. We want to use them as they are. We want to have them young. We want to have them as pure, agile stem cells. And we want to use them in an approach we call the Trojan horse approach. So we take the mesenchymal stem cells, we arm them to send them into the battle against cancer. And our armory of choice is a protein called TRAIL. It is a death ligand which kills cancer cells but leaves normal cells unharmed. I come to that later. So our idea is we take the MSCs, we arm them, so we use them as Trojan horses and let them deliver our drugs in the body to the tumor. And this is again an overview of our armory, which is TRAIL. TRAIL is a death ligand which binds to the TRAIL receptors, which is on cancer cells and other cells, but it selectively induces apoptosis on cancer cells. So it's often seen as a sort of a silver bullet, and that's why we're using it. And of course, we have to make these MSCs express TRAIL. MSCs cannot be manipulated as easily as other cells, so we have to generate a virus, an adenovirus, which expresses TRAIL, or which leads to the expression of TRAIL when the MSCs are transduced with the virus. So we make a DNA construct for TRAIL, integrate it into an adenovirus, give it to our MSCs in culture, and after 24 hours, they start expressing TRAIL. So they're ready to kill the tumor cells. And this is something we're currently establishing. We are testing our MSCs expressing TRAIL in different in vitro settings for prostate cancer, to see whether prostate cancer cells die, how we can improve the TRAIL, how we can improve the targeting to the tumor cells. So we're at all of the preliminary steps at the moment, and our final goal is to inject these MSCs into into patients, into prostate cancer patients, where we expect the MSCs to seek for the tumor cells, migrate towards the tumor cells, integrate in the tumor, and start destroying the cancer. And this work is funded by Prostate Cancer UK, and that's where we are at the moment. So I hope I could give you an idea what type of cell therapy we are trying to establish, and that's what we're doing now. Okay, thank you very much.
Any question for Andrea?
How would they like clock on to go towards the cancer cell? What attracts them to the tumour cells?
Everything is based on the fact that they sense the tumor as a wound.
Okay.
So they recognize the tumor by, oh, there's a wound, I have to go there, I have to repair it. And that's their normal function.
So it's automatic, like it was going to do that anyway?
Yes.
It just happens to express
Yes.
this.
Yes.
Oh, right.
That's what we don't know at the moment, because it hasn't been, the trail expressing MSCs haven't been in humans so far. There is a clinical trial in London going on for the treatment of lung cancer with MSCs expressing trail, but they are recruiting at the moment, so they are awaiting results. Yeah.
How long do you think it will be until this can be brought into everyday practice?
Whether it can be into everyday practice, I don't know, because it's a very, very expensive therapy. Because it has to be tailored to the patients, because you have to get the MSCs. Depending on whether you use patient-derived MSCs, which requires quite a long time to manipulate the cells, to expand the cells, and then give them back. So this depends on how well the patient is, whether there's enough time. Or it depends on stem cell donations. And again, you have to expand the cells, you have to manipulate the cells. That takes time. On the other side, there is a way to work this therapy a bit towards off-the-shelf therapies. This is by using induced mesenchymal stem cells. So you start with an artificial stem cell, an induced pluripotent stem cell, which you then differentiate along the lineage towards mesenchymal stem cells, which you then can manipulate. And this would be something you could produce in advance. It's much cheaper than the first two ideas, because the first two depend on patients, donations, purification, everything, whereas this can be done in a larger scale, in bioreactors, produce them, and have them on the shelf, just take one, do it. Like basically what you do with the CAR T cells. So they can be produced much more easily now than 10 years ago.
Is it been tested in animals already?
Yes, it's working good. It shows fantastic results. Yeah, it has been tested in mice for pancreatic cancer, for lung cancer, and will be done for prostate cancer.
You showed that when we add genetic so that's anything that's helping in like pesticides and stuff. And because when we have tumor in our body, it generates also pathogenic environment, right? Why that cells don't differentiate the processes with you instead of killing? Because the before you cell, reason how to
These cells should behave like
because it generates erythrocytes and most of that in the dishes
yes.
because of the genetic factors that you that is specific for erythrocytes.
I don't add genetic factors. I just add, for example, for the differentiation into fat, I add insulin. So just cytokines. So I don't manipulate them.
Oh, okay.
It's very easy. It's the one gets dexamethasone, the other one gets insulin. So it's just a few factors which make them differentiate. For murine MSCs, it's even much easier. You let them starve, and they differentiate into adipocytes. So they're a bit pre-programmed.
That's
Great.
interesting. Okay, it doesn't matter what therapy we give to patients, you always get therapy resistance. So is there any evidence that this is going to be different? Do you actually see then in your experiments you start to see resistance occurring, and can you preempt that and think, well actually this is what's happened, we can counteract that?
There are two aspects. One, in tissue culture, I see resistance against the tray treatment, and there are ways to overcome this resistance. This seems to be, however, different in vivo studies, where the trail seems to be much more potent when the cells interact with each other. So this needs to be shown